As we have studied in the last year that the flip-flop can be used as a memory element. These flip-flops can store a single bit of data. Here in this example, D flip-flop is shown which can store a 1 bit of data. When the enable signal is high, the data can be stored on the flip-flop. The data is available for read at any time from D output. In the second image, we have shown two tri-state gates to control the read and write process. It is again a D flip-flop with a tri-state input and output. These gates avoids any accidentally returned data or the reading of the data on the flip-flop. These are active low signals and that is why they are called as RD bar or WR bar. So RD stands for read signal and WR bar stands for write signal, and bar indicates that it is an active low signal. Whenever WR bar signal is active low, data is written on the D flip-flop. And whenever RD bar signal is logic 0, data can be read from the flip-flop. Now we can imagine that if we connect many flip-flops together, we can save large amount of data. That is, we can increase the size of memory. So if we connect many flip-flops together, we can have a large amount of memory. Here in this slide, we have connected 8 flip-flops together to store 8 bit of data. Here in this combination, the read, write and the enable signals are common for all the flip-flops with a tri-state input and output. I indicates the input ranging from I0 to I7, whereas O indicates an output ranging from O0 to O7. These are the output lines. The memory which stores a 8 bit of a data is called as a register. Now you can imagine that if we connect all these 8 bit registers together, we can have a large amount of memory where we can store a large amount of data, which is as shown in the figure. So this each 8 bit register is consist of 8 flip-flops connected together, as we have seen in the previous slide. Now this memory has some signals called as address lines, data lines and read-write control signals. In the diagram, the memory is shown. This memory has 2-bit address line, that is A0 and A1. Now if we calculate the number of locations that it can find, that is 2 raised to 2 and that is 4. So here also we can say that we have a register number 0, register number 1, then register number 2 and register number 3. So we can have 4 memory locations. On the left hand side, we have shown this location from ranging from 0 to 3. Now these address lines are connected to 2 to 4 line decoder. Now this decoder will decode the particular address. When the address lines are 0, 0, location 0 will be selected. When the address line is 0, 1, then the register 1 is selected and so on and so forth. If the read signal is generated, then the data available on the data lines read from O0 to O7. If the write signal is activated low, then the data is written on the particular location. When the data is written on the chip, the input signal I0 to I7s are used. These are the input lines for writing a data. Similarly for other locations. So in the case of memory, the first of all the address is generated and the data is either read or write on that particular location. So this is how the memory works, whether it is a RAM or whether it is a ROM. The chip select signal is used to select the particular chip. Memories are always shown as a block with the necessary signals like address lines, data lines and the control signals like read, write and chip select, whether it is a ROM or whether it is a RAM. The CS bar is a chip select signal. It is used to select one of the chip present on the motherboard, as there are many ICs present on the motherboard. To select one of this chip, the chip select signal is used. On the motherboard, every IC has this signal. The number of address lines in the memory for the IC tells you that the capacity of that memory. Like if IC has 10 address lines, then 2 raised to 10, we have 1024 memory location. Likewise, if we have 16 address lines, then 2 raised to 16, we have 65,536 memory location, and in short it is called as 64 kilobytes of memory or the locations. There are commercial EPROMs, those are available in the market, and those are 2732, 2764 and 27128 that we are going to study in this lecture. Now here 27XX stands for EPROM, or it is also called as UEPROM that we have studied earlier, which is as shown in the figure. The next two digit after this tells you that what is the size of that EPROM. That is, if I take in case of 2732, means that it has 32 kilobits of memory. Now if we collect 8 bit of memory of a register, then it becomes 8 multiplied by 4 kilobytes of memory. A byte is a combination of 8 bits. Similarly, if I take a case of 2764, it means that 27 means it is UEPROM and 64 means 64 kilobits of memory. Now if I calculate this in a byte manner, it becomes 8 multiplied by 8 kilobytes of memory. Similarly, if I go for 27128, means that it is EPROM and 128 kilobits of memory. If I calculate in a bytes, then it becomes 8 multiplied by 16 kilobytes of memory. Here you can see that in the animation that A14, A13 and A15 remains constant, and that is 0, 0 and 1. Whereas the address ranges from 0 to all ones. That is, address lines A0 to A12 will be changed from all zeros to all ones as shown in the figure. Here we can make a group of 4 bits and find out the hexadecimal equivalent of the address. For all zeros it will give us the lower address, and for all ones it will give us the higher address. Here for the lower address is 2000H and higher address is 3FFFH. So we can say that the address range is from 2000H to 3000H. In the next interfacing example, we have taken 27128 IC. Now, instead of a decoder, we have used an AND gate in this case. So as we know that the 8085 microprocessor has 16 address lines, so the address space is 2 raised to 16 and that is 64 KB. Now, if we want to interface 27128 IC, we require 14 address lines. So that is 2 raised to 14, that becomes 16384 memory locations, or we can say a 16 kilobytes of memory. The remaining address lines, that is A14 and A15, can be used to generate the chip select signal. Here in this diagram, the address lines A14 and A15 are connected to the NAND gate. When A14 and A15 are logic 0, then the output of the NAND gate becomes a 0, and that is how the chip select signal is generated. Here you can see that in the animation, the A14 and A15 remains the same, that is 0 and 0, whereas the address ranges from all zeros to all ones, as we have seen in the previous slide. That is, the address lines from A0 to A13 will change from all zeros to all ones. Here we can make a group of 4 bits to find out the hexadecimal equivalent address. If we take all zeros, it will give us the lower address, and if we take all ones, it will give us the higher address. Here, the lower address is C0000H and the higher address is FFFFH. Now we can say that the address range is from C000H to FFFFH. Here we can say that H stands for hexadecimal number. Now here in this example we are again using 27128, but instead of using an AND gate we are using 2 to 4 line decoder. Now in this decoder the enable line is already grounded and A14 and A15 lines are used as input for the decoder. When A14 and A15 are at logic 0 and 1, the chip is being selected. Here you can see that in the animation A14 and A15 remains the same, that is 0 and 1, whereas the address range changes from all zeros to all ones. That is, the address line A0 to A13 will change from all zeros to all ones, whereas A14 and A15 will remains constant. Here we can make a group of 4 bits to find out the hexadecimal address. For all zeros, it will give us the lower address, and for all ones, it will give us the higher address. Here, the lower address is 4000H. H again stands for hexadecimal, and the higher address is 7FFFH, and that is hexadecimal. Here we can say that the address ranges from 4000H to 7FFFH. Here we can say that H stands for hexadecimal number. Now this is how we can interface any memory with the 8085 microprocessor. Here we complete the topic of memory interfacing as well as the unit number 1. Thank you.